So good morning all of you. If someone can confirm that I am audible and the screen is visible. Anyone out of three? Okay, thank you. In the last lecture, we were just defining this strong sense white noise and weak sense white noise. I think this is somewhat clear to us now. We would be writing two more things about the white Gaussian noise, which we generally consider in the communication system. And then we will move to today we will move to the design of the correlator. Basically, we will try to build a theory around correlation and match filtering, and we would simply apply it for the detector design from the next lecture onwards. Okay. From the next lecture, we will be moving towards the last part of the course where we would be studying the passband communication, the modulation schemes, and the detector design finally. Okay, this is what the agenda would be for the remaining lectures. So today, I would complete what we were doing in the case of white noise. So as per the definition, white noise theoretically has infinite average power. Okay, this is what we have really defined. How? I will let you know. See, we said that the power spectral density has to be flat. Okay, and this goes from minus infinity to infinity. This is f, and suppose this is your s of x of f pst. Okay, so the average power p would be integral of this power spectral density t of f, and this will lead to what? If this is, let us say, sum n naught by 2, n naught by 2 integration minus infinity to infinity df, and this is infinity. Okay, this approaches infinity. This is a very high big number. So this is what theoretically we have defined. We said that a white noise process is a process which has a flat PST over the entire frequency band. So this phenomenon, or this, you can say, this definition makes white noise physically unrealizable. Okay, it means you cannot have this. So you cannot have a process which will have infinite power. See, if it has infinite power, then you cannot generate it. So this theoretical framework doesn't exactly fit into the real world systems, because real world systems will always be band limited because of two constraints. Because the hardware constraints as well, you cannot generate signals which are very high in bandwidth. It means they contain the entire frequency band. You cannot generate such signals. And secondly, because of several other requirements, you will be always operating in a band of frequency. Okay. So now our purpose is to study white noise in that band only. Okay, that is what we would do right now. So in practical studies, in the bracket I am writing, that is, we would always be operating in a band. Okay, so in practical studies, we generally assume white noise, or even if we are considering white Gaussian noise, over a band of transmission or reception. Okay, let me write these words fully, otherwise you will get confused with transmitter and receiver. Transmission and reception. Okay, so in order to understand, it means that if we are operating over a band, let us say if you are operating from minus B to B, then we need to consider white noise over this band. So we need to consider white noise over this band only. Over this band only if we are transmitting a signal in this band. So how do we do that? So it means the ideal white noise needs to be filtered. Okay, it means suppose if at all I am operating in this band and I am saying that I am getting a white noise in this, so it would be a filtered white noise. It means this noise will exist from minus B to B. Okay, so let me just, this is from example 1.10 from Haken's textbook. This is a good example. This will really help us understand or will help us in later stages. Okay, so what it does is apply, let us study, suppose what is the behavior of a band limited white Gaussian noise. Okay, let me write it down. Let us study, I will let it through this example. So let us study band limited white noise / white Gaussian noise, but here we will be studying band limited white Gaussian noise. So let me remove this. In this example, it will be a Gaussian case. Okay. So apply. So the example says apply a white Gaussian noise Wt of zero mean and power spectral density of n naught by 2 to an ideal low pass filter. Okay, you apply it of bandwidth B and pass band magnitude response of 1 or unity. It means आपने क्या किया? Suppose this is your YWT, this is your SWF versus F, and this would be somewhat like this because this is an ideal white Gaussian noise. You apply it to a filter. Let us say this filter, what sort of response it has? It is a band limited filter from minus B to B, and it is a response of 1. This is called as a pass band. Okay, this is the pass band. The band of frequencies which it passes with some sort of a distortion, but here we have said that the distortion would be nothing. It would simply pass whatever is there in minus B to B because the gain is 1. Okay, so at the output you will get, you know that if at all in the frequency domain the two responses will be multiplied in order if you want to get a response at the output. So the output would be, so you get a PST. It's like this. Okay, so this would be n naught by 2. This will be SW prime F versus F minus B to B. Okay, so W prime T be the process at the output of the low pass filter. Okay, now you will basically, you will appreciate that whatever base we have built after studying the theory of random processes and especially of the Gaussian random processes, how do we really use it in our systems? Now you can clearly see, we remember that if at all there is a Gaussian process, if you apply it to a filter, it means you do a linear operation over it, the resulting process would also be Gaussian. Okay, so now we can clearly simply write that W prime T would also be a Gaussian process. Okay, so that is the way the theory which we have built really helps us in studying all the practical systems of interest. Okay, so let us write it more specifically. So S of W prime F is what? Is N naught by 2 for frequency lying between B to P and is 0 for mod F greater than P. Okay, that is simply what is drawn here. Now let us take the inverse Fourier transform. Okay, take the inverse Fourier transform of the PST. We obtain autocorrelation as see, we have yet not said, I think stationarity assumptions, wide sense stationarity assumptions are inherent. Okay, I am not stating them because this pair, that PST and autocorrelation will be a Fourier transform pair, is under certain conditions. Okay, and that conditions we assume are met here. It would be because it's a Gaussian process we are considering. Okay, as Rn, you can say R of W prime tau would be integral minus B to B N naught by 2 e raised to power j 2 pi f tau and d of f. Okay, you take the simply this is the inverse Fourier transform formula, and you will see that I am not evaluating it, but you will get the answer as n naught into p sinc of 2 pi 2b tau. Okay. So now you realize that autocorrelation function for the ideal white Gaussian noise or ideal white noise is nothing but the delta function. Okay, this is what we have studied. Let me just go back to the notes. Even in the case of strong sense, we write that they have to be independent. Okay, in the case of weak sense, we said that the autocorrelation, this covariance should be sigma square for t equal to s, and for t not equal to s, it should be 0. Okay, that means this is a delta function. I think I must have written it somewhere. Okay, it must be in lecture 22. But anyways, we have said that they have to be uncorrelated, strictly uncorrelated. If at all it is an ideal white Gaussian noise or white noise. But now you realize that after passing it through a band limited filter, correlation gets introduced. Now RW prime tau is no more a delta function. Okay, for tau not equal to 0, you will get non-zero values. So let me write it down. So RW prime tau is not equal to 0 for tau not equal to 0. It means अगर आप tau value 1 put करेंगे या 1.5 या 2 या 2.5, you will get some value. Okay, it means now no longer the process has the property that even how many closer the samples you take of the process. It means if I take W prime T and I take W prime T plus delta T, they would be correlated. Okay, because of the filtering operation. Now, how do you handle? Now, what can you say about the noise? So we will see what happens. Okay, so let us draw this. I think this we have done it several times, but in order to get the context clearly, I am drawing it again. This is the graph of the sinc function. Okay, and this basically this goes on. The lobes may be somewhat bigger as, but the point should be clear. Okay, 1 upon 2p, and this is minus 1 upon 2p. Okay, this is 1 upon b, and this is minus 1 upon b. This is 3 upon 2b minus 3 upon 2b. Okay, this is 0. This is RW prime tau. Okay, and this is tau. This goes on. So what do we observe from this autocorrelation? I will write it down. Okay. So this says that RW prime tau has its maximum value as its maximum value of N naught B. Okay. I think I have not yet, okay, since I have not yet drawn here, this is nothing but N naught. Okay. when not be at the origin. At the origin, and it passes through 0 at tau equal to k upon 2p. Okay, where k is equal to 1, 2, 3 and so on. Okay. Now you see that if at all the spacing or the time spacing is 1 upon 2b, 1 upon b, 3 upon 2b, okay, at these instants the variables become uncorrelated. Otherwise they are, or the process is uncorrelated with these shifts. But if the shifts are not in the multiple of 1 upon 2b, then the process displays correlation. Okay. Now first let us write a few more aspects of this. Since Wt is Gaussian, I think I am just reiterating it what I already said. It follows that this is a very good example, and this forms the basis for the receiver design. Okay, and this as the you can say people with knowledge of digital communication, which you would be after the course is done, you should know this. Okay, it follows that the band limiting noise, the PL noise, W prime of t at the filter output, is also Gaussian. Okay, that we have already, I think, written in, I think I have not proved that theorem, but I wrote it. So you can take it directly from there. Okay. I will see previous lectures. Okay. Now, if what do I do is now sample W prime t, okay, at the rate of 2b times per second. Okay. Now from RW prime tau, what do you see? We see that resulting noise samples, okay, are uncorrelated. So basically what we are doing is we are obtaining W prime, you can say n is equal to W prime, basically you will say n upon 2p. Okay, I should not write W prime n. This should be sampled. I think we should write s. Okay. So this is a, for n is equal to, you can say here should be plus minus, it will be better. No, it should not be plus minus. This n should lie from minus infinity to, n will be somewhat like this, minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay, set of integers. तो आपने क्या किया, आपने W प्राइम टी को, यानी जो हमें W प्राइम टी ये फिल्टर के जो आउटपुट में आया, लेट मी राइट इट एज W प्राइम टी इज द आउटपुट. ओके, सो W प्राइम टी को आपने सैंपल किया टाइम डोमेन में. आपने कैसे सैंपल किया? यू पुट t as n/2b. So basically you are collecting for, in 1 second you are collecting 2b number of samples. Okay, so and I define this as a discrete time stochastic process. Now this is nothing but a, for each n W prime n is a random variable. Okay, why? Because this is from the properties of random processes. Okay, so if you fix the time in the case of a random process, so W prime t is a Gaussian random process, and I am evaluating the value at a particular time t, where t is nothing but n upon 2p. So we know that if you fix time, then W prime n would be a random variable. So we are studying what would be these random variables. Now consider these two random variables, W prime n and W prime n1 and W prime n2, where n1 is not equal to n2. Okay, then we know that what would be the autocorrelation or the cross or you can say the correlation between W prime n1 and W prime n2, that would be 0. Why? Because we know that W prime t, if at all this tau is a multiple of 1 upon 2b, the correlation is 0. Okay, so W prime n1 and n2 would be uncorrelated. So W prime n1 and W prime n2 have a 0 correlation as they are separated. So that is what we want. I have written here. So we see that the resulting noise samples are uncorrelated. Okay, and being Gaussian, so we know that they are Gaussian. Why? Because it is a Gaussian random process, and I am sampling Gaussian random process, so I will obtain Gaussian random variables. अब नाउ क्वेश्चन उठता है ऐसा क्यों? इसके लिए आपको किस पे जाना पड़ेगा? इसके लिए आपको थ्योरी ऑफ गॉसियन रैंडम प्रोसेस में जाना पड़ेगा. उसमें हमने क्या कहा था? If you remember, I will write it. I will show it to you. So a random process xt is said to be Gaussian if the random variables, जैसे आपने टाइम पे सैंपल किया उनको, they have an n-dimensional Gaussian PDF or they are jointly Gaussian. Okay, तो तभी वो एक गॉसियन रैंडम प्रोसेस होता है. अब जॉइंटली गॉसियन कह दिया है तो वो तो एक स्ट्रॉन्गर अजम्पशन है, क्योंकि इंडिविजुअली तो वो गॉसियन रैंडम वेरिएबल्स ही होंगे. ओके, सो हर चीज का एक कारण है, ऐसे नहीं है कि वी आर जस्ट राइटिंग इट एज इट इज. वी नीड टू हैव अ थ्योरी व्हिच लेट्स अस से दैट ठीक है ये होगा. ओके, एंड दिस इज इंपॉर्टेंट at the UG level, at the undergraduate level, even to know what theory is. You may not be quite conversant with the proofs. Okay, proofs आप थोड़े बहुत कर सकते हैं, थोड़ा छोड़ सकते हैं, that is absolutely fine. But at least you must know कि ये चीज कहाँ से आई है, because we are engineers, we are not diploma holders who just need to apply things. We need to learn as well that how our fellow engineers develop this. Okay, so that is the difference between an engineer and diploma holder. We are just not the people who will basically repair things, or we will be making new things as well. Okay, so I think and being Gaussian, they are statistically independent. Okay, this follows from the case where we had wrote an exception that it doesn't mean that if the random variables are uncorrelated, they would be independent. Although it holds that if they are independent, they would be uncorrelated. It holds. But vice versa, it doesn't hold. That uncorrelated implies independence. But there is one exception, and that exception is in the case of Gaussian random variables. If at all two Gaussian random variables are uncorrelated, okay, or pairwise if the random variables are uncorrelated, Gaussian random variables, then they would be independent as well. Okay. So Gaussian random variables के केस में अगर आपने uncorrelatedness prove कर दिया, तो it will directly imply independence. Okay, they are statistically independent. Now why we are considering this sampling? Ultimately हमने sampling क्यों consider किया, जबकि हमें पता चल गया कि process में अब correlation आ चुका है. ये sampling हमने इसलिए consider किया है because receiver पे हम ultimately sample data पे ही काम करते हैं. Okay, so that is the reason we are now considering sampled filtered output. Filter का जो output आया उसको हमने we would sample it. Okay, so like writing the final comment on it. So note that each such noise sample has a mean of 0, has a mean of 0 and variance of N naught P. Okay. Now this is, I am writing, say it from R W prime 0. But this essentially, this comment is a homework to verify. Okay. This may come up in the exam as well. Homework to verify. How do you say this? Homework is to verify. So the homework is that you have to verify the statement. Verify this statement. So it means जो हमने यहाँ पे WS prime n लिखा है, so WS prime n would be a normal random will mean 0 and variance and not B for all n. Okay, for all n being integers. So जो random variables आएंगे ये हर एक n के लिए, जैसे n1 है तो वो भी एक random variable होगा जिसका मीन 0 होगा और वेरिएंस नाउ n नॉट इंटू p हो. So ये याद रखना बहुत जरूरी है कि इसकी वेरिएंस अब बदल जाएगी, वो n नॉट इंटू p. ठीक है. So this is what we wanted to do in the case of white noise or white Gaussian noise. So we are done with this concept. Now we move ahead with the concept of correlation. Okay. So more or less by now we have closed our discussion on all the aspects of random processes required for the course. Okay. अब हम लोग रैंडम प्रोसेस को बस रेफर करेंगे, नया इनके बारे में कुछ ज़्यादा नहीं जानना है. We would be doing one more thing, I think maybe next class or so, where we would be studying pass band. Okay, how do you basically set up the equivalence between baseband and passband? Okay, that is very very important for us to know. We may not be very much conversant with the proof, but we must know कि उसको एक्सप्रेस कैसे किया जाता है. इससे क्या होगा, what would the benefit, that whenever you will go back and read textbooks, see all the UG textbooks will contain this, so you are not lost that what we are doing. Okay, so this is the case. So let us do the correlation. Now this is what is called as a correlating receiver or ultimately a matched filter. तो ये random process की theory, जब when the random process theory closes or it is towards the end, we do this. Okay, and this will inspire all of our receiver design. So I'm writing it down. You can just study it or just follow a typical. This I am particularly taking it from Upamanyu Madhav's book. Why? Because he has given it in a very, you can say, I won't say easy manner, but a manner which suits our purpose. Okay. Okay. Otherwise, if you go to Haking or if you go to other textbooks we are referring to, they would contain the proper derivation of it. Okay, and this at the UG level doesn't help us. Although in a course at the PG level, this proper derivation we do because there the concern is more or less on knowing the proofs and doing the proofs. But here we must understand the concept at the UG level. And proofs in a lighter sense will also work. So I have done this in our course. Sometimes I prove things in a lighter sense, sometimes in a more involved sense. Okay, so the same approach we follow for the correlation. So a typical operation in a DC receiver, digital communication, or I should write digital communication, otherwise people will feel this is direct current. Communication receiver is to correlate. Receiver is to correlate a noisy received waveform against one or more noiseless templates. Now, what is the purpose is, let us say you are receiving something, okay? So you will find that in most of the digital communication receiver, you would be correlating it with something. Why this happens is, because in a digital communication, DC, you transmit from a finite set of signals, okay? That is, आपके पास एक सेट है, you have S1T, because it's a digital communication system, so you have already sampled the information and you have encoded the information. So once you do that, you have limited the set from which you will transmit something. That is the difference between analog communication and digital communication, and we have gone through it in the first, I think, 1 or 2 initial lectures, where we said that it would be some sort of a finite time, finite amplitude thing, okay? Or you will have a finite amplitude, means you know that what are the possible signals which you would be transmitting. So you have a set. Let us say that set has n members, okay? So every time you would be transmitting one of these signals. Now what happens that once this signal is transmitted, if at all, let us assume it is going over a wire, okay? Now because this is going over a wire, and let us say this is the transmission module, and there is a wire, which is a receiving module. So here there will be a circuit, and here also there will be a circuit. Now in these circuits or over the wire, there will be random motion of electrons, okay? Because ultimately electrons are the, you can say, the sole carriers, or because of their motion only the signal is moving, okay? Their random motion adds up a noise to the received signal, okay? If I receive a yt, that would be some s of it added with the noise, okay? This is noise. And it is, I think we are not going into that, but it is shown, or it has been shown, that this noise has some sort of a white property. It means it is like a white noise, and because of the central limit theorem, it can be well approximated to be a white Gaussian noise, okay? Now the transmission का set था वो तो finite था, it has capital N elements. But what about this? Now this does not belong to a, this does not belong to a finite set. Now, then this is the problem at the receiver. Now, receiver is in dilemma. What should I do? Now, since this is a finite set at the transmitter, this is known by the receiver as well. Okay, receiver knows this. What are the possible signals from which my transmitter can send us information? But the issue is, अब कौन सा ट्रांसमिट हुआ ये कैसे पता चले? तो उसके बाद बेस्ट स्ट्रेटेजी क्या है कि जो ये टेम्पलेट्स हैं, यानी कि जो पता है कि यही वेवफॉर्म्स आ सकती हैं, हर वेवफॉर्म का रिसीवर के साथ कोई ना कोई, यू कैन से, कोरिलेशन फाइंड करके चेक करें कि कौन सी वेवफॉर्म सबसे ज्यादा कोरिलेटेड है रिसीव वेवफॉर्म से, मींस व्हिच ऑफ द ट्रांसमिटेड वेवफॉर्म इज most correlated with what I receive. If I find that, let us say that metric I develop as correlation. So if I find that S3 is giving me the most correlation, so I will claim that S3T was transmitted. Okay, because I have no means to eliminate NT. The reason is I don't know NT. Okay, so the problem is I may be knowing, or I know, maybe knowing. I should not confuse by writing maybe. It should be that I know the set of transmitted. I know the set from which transmitter sends the information, but by no means I can know NT. Okay. Now this is the case. If I don't know NT, then I cannot eliminate it. Okay, इसको हटाया नहीं जा सकता. इसमें से बस एक काम किया जा सकता है. We need to do something at the receiver which basically reduces my probability of error. It means error कैसे होगा? Suppose आपने S2 को ट्रांसमिट किया, बट आपने जो भी प्रोसेसिंग किया रिसीवर पे, उसकी वजह से आपने S3 को क्लेम किया कि मैंने S3 ट्रांसमिट किया. Now this is an error. Well, S2 was transmitted, but I am claiming S3T was transmitted. So somehow I need to design a receiver in which my error of, that is my probability of committing the mistake is reduced. Okay, so this is what we need to do. So mostly it involves an operation where we correlate the set of possible signals to the received waveform. Okay, this is what is written about. So let me move ahead and see. So correlation with this background, I think we'll appreciate what we're doing. So correlation of yt against g of t, let us say a random anything, any signal g of t is defined by the inner product between y and g, and that is defined like this. So for continuous time signals, this is like y of t g star of t dt. So right now we have not yet said if y and t are real valued or not, but in the most general sense, it would be defined like this, where g of t, this is the complex, basically this is the conjugate operation. So this says that mostly, in a lot of cases, y and t would be complex signals. So this is the most general definition. If it is not complex, then this star is removed, because for a real signals, g star t is same as gt. Okay. So this is what the correlation is. So considering y of t as s of t plus n of t, okay, and all signals of interest, all signals to be real, with st being deterministic, deterministic, it means I have already told you that st can take possible values in any of this set. It means from the set it can take a possible value, okay, and nt being random, okay, and nt being zero mean white noise with PST Sn of f is n naught by 2. Okay, this is the parameter. Well, this has been given to you that nt is a zero mean white noise with PST. There is a question that why always we take noise to be zero mean, because no difference would be, if at all there would be a mean, but because it is completely random and the uniformity it has, considering it to be zero mean is beneficial, as well as this makes its first moment independent of time. Okay, and this is what the stationarity concept is, that your weak sense stationary process needs to have the first moment and the second moment to be independent of time. So it helps us in that also. If we say that the zero mean, so आपका first moment जो है NT का वो एक independent of time हो गया. Okay, आप एक वैल्यू भी दे सकते हैं कि आप कहेंगे that is a mean of 1, is a mean of 2, but then it says that कोई bias है इसके अंदर NT के अंदर, but NT एक completely random phenomena है जिसके अंदर एक sort of uniformity है in PST, so it would be better if you consider it to be zero mean. And this also says that it doesn't shift the mean of whatever you are transmitting. It only changes its variance. Okay. क्योंकि mean of yt क्या रहेगा? Mean of yt would be the mean of st only, but the variance of yt won't be the variance of st. Now variance gets changed because of the addition of nt. Okay. So let us now suppose this is z, which is the correlation of y with g. So what you get is s comma g plus g. Okay. So this is nothing but integration minus infinity to infinity s of t. See, this inner product and everything I wanted to introduce when we were doing the concept of orthogonal projection. Okay, For this, you can refer to BP Lattice chapter 2. I would write. That would be better. Because we didn't cover it that time, because you have already done a course on groups and linear algebra. So I thought you would easily understand it, or you will be already knowing it. But for those who are interested, or those who want to revise this, or those even who don't know it, they can see chapter 2 from BP Lattice textbook. Okay. It is written quite well there. You will get to know what is the inner product, and how do you set up an analogy between vectors and the signal space. Okay, signal space means the space, the vector space in which your vectors are signals. Okay, that is what you can say. Plus integration minus infinity to infinity n of t g of t dt. ओके, तो हमने क्या किया, जो रिसीव सिग्नल निकला y था, उसको हमने एक सिग्नल gt से कोरिलेट कराना है, तो हम उसका एक्सप्रेशन लिखना चाह रहे हैं अगर yt इस तरीके का है तो इफ yt इज st प्लस nt, तो g से अगर कोरिलेशन कराएंगे तो क्या आएगा ना, एक फिनोमिना ऑब्जर्व कर सकते हैं हम लोग, विल स्केलिंग gt डज अ डिफरेंस. ओके, अब नॉइज का भी कोरिलेशन हुआ gt के साथ और सिग्नल का भी कोरिलेशन हो रहा है gt के साथ, पर क्या अगर हम gt का एम्पलीट्यूड चेंज करें तो कुछ बेनिफिट होगा? कोई बेनिफिट नहीं होगा, बिकॉज इफ एट ऑल यू स्केल gt, it scales the signal part as well as it scales the noise part, so there is no benefit of scaling gt. means उसका एम्पलीट्यूड बढ़ा के कुछ नहीं मिलने वाला है. So scaling gt, so this is the way Upamanyu Madhav basically gives this. Okay, and this is also a good way to understand. Otherwise, it has a very standard derivation through the inverse Fourier transform concepts and everything. But this derivation, through this derivation, you can appreciate whatever concepts you've gone through in vector spaces. Okay. Now scaling gt scales both S and N, basically ST and NT, equally. Okay. Hence, performance metric of interest is the ratio of the signal power to the average noise power at the output of the correlator. Okay, we will see it, what we are saying. देखिए, what it would be, this would be a number. Okay, and this would also be a number. First of all, z क्या है? z एक नंबर होगा, z एक सिग्नल नहीं है टाइम का, बिकॉज टाइम वेरिएबल इज ऑलरेडी इंटीग्रेटेड आउट. नाउ if at all this z is a number, so I want to see in that number what is the contribution from st and what is the contribution from nt. If in that number I can reduce the contribution of nt and increase the contribution of st, then if I do a detection based on z, I might land up with the correct answer, or this should be the intuitive approach, क्योंकि scaling से तो benefit नहीं है. If I scale gt, this scales this part also and this scales this part also. Basically, this ultimately scales the addition of two. Means अगर आप gt की जगह a times gt put करेंगे, so a will come outside and this will be a bracket. So that is no benefit. So let us see कि basically gt का जो correlation हुआ st के साथ, जो ये नंबर आया और जो ये नंबर आया, सो हम इन दोनों नंबर्स का रेशो देखना चाहते हैं और इस रेशो को बढ़ाना चाहते हैं. इसके बढ़ाने का बेनिफिट क्या है कि जो आउटपुट का नंबर आएगा उसमें इसका कंट्रीब्यूशन ज्यादा आएगा और इसका कंट्रीब्यूशन कम आएगा. मतलब हमें ऐसा जीटी चूज करना है जिससे this number divided by this number is maximized. Okay, and the benefit is Z will have more contribution from S. So Z will give us a decision statistic. It means एक number मिलेगा जिससे हम अगर फैसला लेंगे, we will try to say that what was transmitted. हम ST की आइडेंटिटी के बारे में कुछ बोल सकें तो बेनिफिट रहेगा. That is what the meaning of saying is. Okay. ये सब नंबर्स हैं. ये सिग्नल पावर जो होगी मोस्ट इट वुड बी द इंस्टेंटेनियस. लेट मी राइट इट डाउन. Basically square of the value of the output. Okay, this is nothing but square of the value of output. Mod square नहीं ले रहे हैं because ये real framework है. ये simple इतना है. और average noise power क्यों कह रहे हैं? Why are we saying average noise power? Because whatever we get, this would be a random variable. Okay, although it would be a number, but it would be a random variable because NT keeps on changing. Every time whatever NT you observe is a sample function of the white Gaussian noise process. I think sample function हम लोगों ने डिस्कस किया था. sample function क्या है कि कोई भी जैसे आप 9 बजे से लेके 10 बजे तक रोज रिसीवर को ऑन करते हैं और कुछ भी ट्रांसमिट नहीं करते हैं, तो जो रिसीवर पे वेवफॉर्म आ रही है वो एक टाइप का नॉइस वेवफॉर्म है. फिर अगले दिन आप 9 से 10 के बीच में आप फिर रिसीवर को ऑन करते हैं, ट्रांसमीटर अभी भी ऑफ ही है, तो जो वेवफॉर्म आ रही है वो एंटी आ रही है. पर ये दो वेवफॉर्म दोनों दिनों की अलग अलग होंगी बिल्कुल. यानी कि जो आज 9 से 10 के बीच में मिली और जो कल 9 से 10 के बीच में मिली वो बिल्कुल अलग है. तो ये जो हम रिसीवर डिजाइन कर रहे हैं, सर्किटरी तो बदलेगी नहीं बार बार, सर्किटरी तो एक ही रहेगी. तो उस सर्किटरी में ये जो चीज है ये रैंडम वेरिएबल होगा. आज ये कुछ आएगा, कल ये कुछ आएगा. तो इसके लिए हमें इसका एवरेज नॉइस पावर लेना पड़ेगा, मतलब इस रैंडम वेरिएबल का एवरेज नॉइस पावर. उस रेशियो को हम मैक्सिमाइज करना चाहेंगे बाय अ इंटेलिजेंट सिलेक्शन ऑफ जीटी. ओके, दैट इज व्हाट वी आर डूइंग. So what is the SNR? Let us define this as the SNR. We define this. It हम कह रहे हैं कि जो नंबर आए उनका रेशो को हम, उनके स्क्वायर को रेशो को हम SNR बता रहे हैं. तो जैसे हमने S, G इनर प्रोडक्ट लिया, उसका एब्सोल्यूट का होल स्क्वायर. ओके, बिकॉज दिस कैन कम आउट टू बी नेगेटिव ऑल्सो. आप बेसिकली इसको होल स्क्वायर भी कर सकते हैं, बट सपोज अगर हम कॉम्प्लेक्स फ्रेमवर्क को भी रोल में लेके चलें तो इसलिए फिर मॉड स्क्वायर करते हैं. एंड देन वी हैव टू डू द एक्सपेक्टेड वैल्यू. I think I have explained it that why we have to take the expected value, because this thing is a random variable. Because n of t would be a sample function. Okay. Of the random process. Okay, so the problem is, so choose G in order to maximize the SNR. तो उसका इंट्यूटिव रीजनिंग हमने बिल्ड कर लिया है. वो क्यों? क्योंकि अगर आपने जी ऐसा चूज किया जिससे आपने इस क्वांटिटी को मैक्सिमाइज किया, तो अल्टीमेटली जो जेड आएगा उसके अंदर कंट्रीब्यूशन फ्रॉम सिग्नल वुड बी मोर एज कंपेयर टू कंट्रीब्यूशन फ्रॉम नॉइस, एंड दिस वुड बेसिकली हेल्प अस टेक बेटर डिसीजंस, और आई वुड से दिस वुड हेल्प अस रिड्यूस द प्रोबेबिलिटी ऑफ एरर. मतलब चांसेस जो एरर होने के हैं वो घट जाएंगे. यही बचता है हमारे पास. अब इसमें समस्या क्या है? हमने लिखा है एंटी नहीं पता हमें. अगर एंटी पता होता तो किस तरीके से हम उसको एलिमिनेट करते. मतलब अगर एंटी आल्सो बिलोंग्स टू अ डिस्क्रीट सेट, इट मींस जैसे S1, S2, SNT दे बिलोंग, मतलब ST व्हाटएवर वी आर ट्रांसमिटिंग विल बिलोंग टू आइदर ऑफ द सिग्नल्स. ओके, S1, S2, SN. बट एंटी नहीं पता. एंटी रैंडम प्रोसेस है, उसके इनफाइनाइट सैंपल फंक्शंस हैं, वो कुछ भी हो सकता है. ओके, सो अब हम G को कैसे चूज करेंगे? तो यहाँ पे हमारा जो वेक्टर, अब दो चीजें हेल्प करेंगी हमारे यहाँ. दिस इज अ वेरी वेरी गुड, आई वुड से, डेरिवेशन, and a very simple one. That is what Professor Madhav has done, and this is quite good. So let us find this out. First of all, ये हम जो डिनोमिनेटर है उसको इवेल्युएट करते हैं. ये क्या होगा? ओके, तो कुछ नहीं है इसमें, आप सिंपल फॉर्मूला पुट करिए. सो दिस इज इंटीग्रेशन n of t g of t dt multiplied by integration n of s g of s ds. ओके, अब ये कैसे आया? देखिए ये क्या है, ये है। अब क्योंकि रियल फ्रेमवर्क है तो एब्सोल्यूट वैल्यू का जो स्क्वायर होगा वो सिंपली प्रोडक्ट हो जाएगा दोनों का। अब ये हमने एस और टी क्यों यूज किया? डिफरेंट वेरिएबल्स ऑफ इंटीग्रेशन, रिमेंबर why different variables of integration. So this is also a small homework, very simple. Okay, I think you may be knowing it. In order to catch all the possible cross terms, if you don't take different variables, most of the cross terms will be missed. Okay. So now take the expectation inside. Now take the expectation inside. Take the expectation inside. Inside the integral. Integrals and group all random terms. Okay. Random terms together inside the expectation. So what do we get? Let us see. So the expected value of double integral expected value of n of t into n of s. Why? Because if I take the expectation, this expectation and integration are interchangeable. I am not basically throwing light on the conditions in which this expectation will go inside. Basically यहाँ पे तो आप बस expectation की linearity property use कर सकते हैं. Basically expectation is a linear operator. Linear operator means if you are taking expectation of ax plus by, then it is simply expectation of ax plus expectation of by. Okay. So because integration is some sort of an addition operation only with a different sort of a setting, so this expectation can go inside easily. बट जो इंटरचेंज का प्रिंसिपल है, जैसे इंटीग्रल और डेरिवेटिव का इंटरचेंज है या लिमिट और इंटीग्रल का इंटरचेंज है, दे कैन नॉट हैपन एज पर आवर विल. देयर आर सेट, यू कैन से, रूल्स व्हिच will tell you that when can you take limit inside the integration or when can you exchange derivative and integration if you encounter such problems. Okay, so do check those conditions before doing any sort of interchange. Then this is g of t, g of s, dt ds. Now why does this happen? Because expectation will go over random quantities only, and in this expression there are only two random quantities. One is nt and ns. gt and gs are deterministic because we have already told that s is deterministic. But okay, so I need to add g is also deterministic. Where I have written it, gt is also you can say that why not GT being a random thing? See, basically we have to design the receiver. So ऐसा receiver जो कि random चीजों के साथ input को correlate करे, वो तो anyways cannot need to optimize. Okay, because already we are suffering from one thing which is random, that is NT. So now here, what would this be? We have said that this NT is a white Gaussian noise. So we know that the autocorrelation is nothing but this. Okay. So it depends on, anyways, this R and T minus S is from the stationarity assumption, and this is nothing but equal to, because it is a white Gaussian noise case, this, or white noise, and not by 2 delta of T minus S. So this comes from the stationarity case, with the stationarity assumption or White's stationarity assumption on NT, because if it is White's stationary process, the autocorrelation is nothing, it depends only on the time difference, and because it is white noise, so the autocorrelation is nothing but the delta function. Okay. Now you put this, so once you put it, you will get that this is equal to double integral n naught by 2 delta of t minus s g of s g of t ds dt. Okay. So if I try to do it, this is n naught by 2 suppose, then this is integration. So integration, suppose this is also some sort of an interesting case. Okay, I can write like that, this is over s and this is over t. Now what is this? This is nothing but the, you can say, the shifting property or the property of delta function, where the output of this would be nothing but g of t. Okay, this integration, and this leads to n naught by 2 integration over t g of t square t of t. Okay. One more thing, I think I need to write this as absolute value square. Why? Because हम लोग स्टार को थोड़ा क्या यहाँ स्क्वायर लिखते थे, जब रियल फ्रेमवर्क लेके चल रहे हैं तो ठीक है, बट इन द टेक्स्ट बुक यू विल फाइंड दैट देयर इज एन एब्सोल्यूट वैल्यू ऑपरेटर है, बिकॉज यहाँ पे कॉन्जुगेट्स आएंगे, वो डेरिवेशन जब कॉम्प्लेक्स केसेस होंगे तो ये जो कॉन्जुगेट है यहाँ पे ये आपका हर जगह आएगा, दिस स्टार. सो ये स्टार यहाँ पे भी आएगा, g स्टार t would be the output, here it would be g star t, and then when g star t gets multiplied with gt, you will have mod of gt square. Okay. So what it is, this is nothing but n naught by 2, and you can write in terms of the norm over the signal space. Let me write, this is norm over the signal space. This you can see in Lathi, see chapter 2. Means if at all you want to deal with this sort of a notation, or you can simply even reject it, you can say ठीक है ये मैं नहीं जानता हूँ, तो आप ये लिख सकते हैं कि n naught by 2 into energy of gt. Basically this is what, this is nothing but you can write n naught by 2 into e of g, ऐसे भी लिख सकते हैं, क्योंकि एनर्जी का फॉर्मूला क्या होता है, एनर्जी इज नथिंग बट इंटीग्रेशन ओवर टी मॉड ऑफ जी टी स्क्वायर डी टी फॉर कॉम्प्लेक्स सिग्नल्स, और रियल हो फॉर कॉम्प्लेक्स, एंड रियल के केस में दिस इज नथिंग बट ऑल वैल्यूज ऑफ टी माइनस इंफिनिटी टू इंफिनिटी है ये. ठीक है, अगर आपको बहुत इच्छा है कि आप नॉर्म वाली नोटेशन को फॉलो करें तो आप ये टेक्स्ट बुक का ये चैप्टर 2 हमने बोले बेसिकली सिग्नल्स थोड़ा बहुत वेक्टर स्पेस वगैरह कर लिया है कोर्स में, ऐसा नहीं है, बट सिग्नल स्पेस को हमने उतना डीपली डील नहीं किया था इस तरीके से कि दैट वी सेड कि जो सिग्नल स्पेस के ऊपर नॉर्म आएगा वो क्या होगा, बिकॉज वी हैव सम सॉर्ट ऑफ यू कैन से बैकग्राउंड ऑफ वेक्टर स्पेसेस, दैट्स व्हाई वी डिडंट गो इनटू बिकॉज वी डू नॉट हैव दैट मच ऑफ टाइम. So इसलिए we left a few things to be self-read. Why? Because the base required for us to read those things is already built through other courses. Okay. Now let us move ahead. Where are we? So SNR now. I think I should write here. This is white sense stationary, and this because of it being white noise. Okay. So that those who will study from the notes, if at all, they know that from where. Basically, n of t is white Gaussian noise, so it implicitly is a stationary process. So the white sense stationary already है. ये लिखना जरूरी नहीं है यहाँ पे कि हम WSS लिखें फिर white noise बोलें. Basically white noise बोला है तो इसका मतलब यही है कि वो एक white sense stationary process होगा. ओके, क्योंकि उसकी कंडीशन ही है, चाहे आप स्ट्रॉन्ग सेंस में देख लें चाहे वीक सेंस में देख लें, इट सेटिस्फाइज द प्रोसेस ऑफ, इट सेटिस्फाइज द कंडीशंस ऑफ stationarity. Okay, so SNR would be nothing but S comma G whole square divided by n naught by 2 into E of G, or n naught by 2 into norm of G square. Now this can be written as twice 2 by n naught means now this SNR reduces to 2 by n naught, the inner product of or the correlation of S with this unit, you can say vector, or you can say this has a unit energy. Okay, unit energy signal you can say, or you can say unit norm vector. Unit norm, sorry, unit vector in signal space. Means alternative notation. अगर आपको signal space उतना नहीं भी, you can say you do not feel that much happy with signal space, you can work with the standard notation also. This is the standard notation, unit energy signal. Unit vector in vector space. So देखेंगे आप SNR ये आ गया. अब क्वेश्चन उठता है हम G को क्या चूज करें जिससे ये मैक्सिमाइज हो जाए. तो इसमें हमारे को कॉची-श्वार्ट्ज इनइक्वालिटी बहुत हेल्प करती है. वो ये कहती है कि अगर आप दो सिग्नल्स का कोरिलेशन ले रहे हैं और वो दो सिग्नल्स का कोरिलेशन कब मैक्सिमाइज होगा, जब दोनों सिग्नल्स अलाइंड होंगे या दोनों वेक्टर्स अलाइंड होंगे. लेट अस से इफ यू आर टेकिंग the correlation of two vectors A and B. So it says that the correlation of A and B is less than the product of, I think, individual nodes. And it says that the equality holds when A and B are aligned. एक डायरेक्शन में होंगे. तो बस this gives us an answer that G needs to be aligned to S or G has to be some multiple of S. Okay, it needs to be in the direction of S. Let me write it down. Okay. So drawing an analogy between signals and vectors. Note that G upon norm of G is the unit vector pointing along G. Okay. We wish to choose G such that the size of the projection, the size of projection of the signal S. So yet we have not yet defined the projection, or in the context of signals, basically this directly follows from the concept of projection we studied for normal vectors. Okay, ये हमने study किया है कोर्स में अपने, when we were, I think, just before Gram-Schmidt orthogonalization process, we studied this. Okay, so you can just go back and read the signal S along the unit vector is maximized. Along the unit vector is maximized. Now how do you do that? It's quite simple. I think let me just show. Suppose आपका एक वेक्टर है S, एक वेक्टर है आपका G. तो हमें पता था कि इस पे जो प्रोजेक्शन होगी वो होगी जिस पे ये ऑर्थोगोनल हो. मतलब ये जो वेक्टर है, दिस इज द एरर वेक्टर. दिस एरर वेक्टर इज ऑर्थोगोनल. Now if at all we want to say that the projection is maximized, so obviously maximized कब होगा, जब error zero. अब error zero होने के लिए क्या है, सिंपली S needs to lie along G, or you can say G needs to lie along S. बेसिकली हमें यहाँ पे G चूज करना है, तो G needs to lie along S. ये काफी सिंपल तरीके से आप ऐसे भी देख सकते हैं. ओके, so this is accomplished. This is accomplished by choosing the unit vector, along the direction of S. Now, why we are saying along the direction of s? Because unit vectors generally indicate direction. Okay, अगर आप देखेंगे तो आप, I think, let me just revise. If you know IJK, which we used to do in our standard 12th, IJK, what were they were? They were unit vectors which simply represent directions. Okay, so that is why we are saying along the direction of s, because now G upon G, norm of G becomes a unit vector. Okay. So we will just close this and then we'll close for today. It's a, so what you have to do is, so choose G. So it is choose G as any scalar multiple of S. Since मीन्स क्वेश्चन तो उठता है कि g अपॉन जी, नॉर्म ऑफ जी को अलॉन्ग s होना चाहिए, ठीक है, ये तो हो गया. बट अब आपको g क्या लेना है, तो ऑब्वियसली g विल बी सम मल्टीपल ऑफ s, बट व्हाट दैट मल्टीपल वुड बी, सो दैट डजंट मैटर, दैट इज व्हाट वी आर राइटिंग. मतलब g नीड्स टू बी सम, बेसिकली g नीड्स टू बी इक्वल टू सम a टाइम्स s. सो व्हाट इज दैट a? Okay, any scalar multiple, so I am writing any scalar multiple, here should be in bracket a of s, since SNR is a scale invariant quantity. Why? Because अगर हमने G को A टाइम्स S भी चूज किया है तो SNR क्या है आपका, उसमें A तो कैंसिल हो जाएगा क्योंकि G अपॉन नॉर्म ऑफ G से आपने प्लॉट ले रहे हैं. तो आप कोई सा भी, you can take any scalar multiple of S as G, but that won't impact the SNR. Only SNR मैक्सिमाइज सिर्फ इस फैक्ट से हो जाएगा कि G जो है वो S की डायरेक्शन के अलॉन्ग है, तो उसमें इस स्केल फैक्टर की कोई वैल्यू नहीं है. Okay. So now substituting, what would be the SNR? So SNR would be equal to twice of norm of S square by. Okay. How do you get it? You can see it from here. Okay. So I think, let me just, one more important thing you should write here, that for complex valued signals, in complex valued white noise, we have not yet introduced complex valued white noise. Once we will do passband, we will introduce it. G would be a scalar multiple of S star T. Okay. Okay. So I think I need to write one theorem for it, but it would be great if you would do it in next lecture, because this will have some sort of an overlap between the lectures. We will revise this concept in the next lecture as well for initial 5-10 minutes, and then you would simply go to the match filter design. Okay. So we are done for today. Those who need to talk on something, they can stay, others can leave. We'll meet tomorrow at 12. Okay.